So these are the working solutions for the formative we just had for dealing with 1.5 to 1.7. So the first question is that we're asked to find the zeros of the function f of x is equal to x squared plus 6x minus 4. So finding the zeros meaning that we really want to find where the answer is 0. So that implies that f of x would be 0. And so in this case, what are all the values of x that makes this equation true? Or in this case specifically, where are all the values of x that makes the equation equal to 0? So there are a few ways that we go off and try to do this. So one of the first ways I might try is factoring. So here we can't factor this because there's no two numbers that multiply to -4 and add to +6. So our next default might be the quadratic formula or completing the square. Most of us have a tendency to sort of just default to the quadratic formula because it's a formula, it's something that we can memorize and sort of pipe through. So that's what I'll do over here. So A is equal to 1, B is equal to 6, and C is equal to -4. So one of the first things I would like to do is just figure out what the discriminant is, because if the discriminant is negative, I don't have to go any further. There are no solutions. So again, the discriminant is b squared minus 4ac. So that's going to be 6 squared minus 4 minus 1 times a minus 4. So here's going to be 36, and it's going to be -4 times 1. So -4 times a -4 is going to be a positive 16. So this is a kind of tricky thing with the quadratic formula. We need to take care of our arithmetic. So a lot of times I see arithmetic errors just dealing with the discriminant and having the wrong sign on the 16 part. So a lot of times, a few times I've seen already, I've seen answers of 36 minus 16, so we just need to be careful. So in this case, we do get 52, so that means there are solutions. In this case, since the discriminant is positive, there's going to be 2 solutions. So another reason why I'm kind of doing this off the side is because it actually makes dealing with a quadratic formula a little bit easier. So the quadratic formula again is minus b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be a -6 plus or minus the square root, and I don't have to do this entire b squared minus 4ac already because I've done it off to the side. So it's going to be plus or minus the square root of 52 all over 2 times 1, which is 2. So remember, we want this in exact form. So this is why we did the lesson on radicals that we did, because we want to have exact representation of a radical. So we do not want to plug this into a calculator, get a decimal answer. We actually want this as a radical, but we do need to simplify this. So here, -6 plus or minus, well, 52 is going to factor into 4 and 13. So it's going to be root 4 times root 13 over 2. So here we get -6 plus or minus 2 root 13 over 2. And now we just have to reduce this fraction. So here I could really factor out a 2 at the numerator, and we're going to get -3 plus or minus root 13 all over 2. And the 2's simplify or reduce, so our final answer is going to be -3 plus or minus the square root of 13. So we could leave that as an answer. We don't have to separate that. Hopefully, as we get more experience with math and looking at these types of answers, recognizing that there is 2 answers, -3 plus root 13 and -3 minus root 13. I do want to take some time to show that we could actually get this answer by completing the square as well. To me, it's a nice, elegant way, and I don't. It's less likely for me to get tripped up all over with the arithmetic inside the quadratic formula. So again, we're going to have x squared plus 6x minus 4 is equal to 0. So one of the steps we want to do sort of in completing the square is that we want to take the 6 divided by 2 and square it. So that's going to be 3 squared, which is 9. So in other words, we need an x squared plus 6x plus 9 on the left-hand side equal sign to make this a perfect square trinomial. Well, in order to get 9 from a -4, I need to add 13. So we're then going to add 13 to both sides. So here you get x squared plus 6x plus 9 is equal to 13. Now the reason why I'm doing a perfect square trinomial is that I know this over here will factor to x plus 3 quantity squared is equal to 13. So now that I have the left side as a perfect square trinomial, in other words, there's one occasion or one occurrence of x. And the reason why I want it in this format is now I could actually square root that. So when I square root of x plus 3 quantity squared, that's just going to be x plus 3. And on the left side, I still get root 13. Another thing that we need to remember is that this is a plus or minus. So the advantage of the quadratic formula is that it's built in to our formula so that we remember the plus and minus. We just have to remember when we do completing the square, when we square root, we also have a plus or minus an answer to this as well, plus or minus root 13. So our last step here is I could break this up into 2, but I'm going to shortcut this a little bit. I'm going to subtract 3 from both sides. So I'm going to get x is equal to minus 3 plus or minus root 13. So we notice that we come up with the same answer at the end. Completing the square in this case worked out nice because 6 I know was divisible by 2. The a was just a 1, so I didn't have to factor anything else to complete the square. And it worked out rather nicely. The second example is here we're given the roots. X is equal to 1 plus or minus root 7. So to me at this point, we're asked for the family of quadratics in factored form. Recognizing there's 2 roots, so I'm going to write this out explicitly. It's going to be x is equal to 1 plus root 7 and x is equal to 1 minus root 7. So those are the 2 roots. So writing out factor form is in general we have f of x is equal to a x minus r, x minus s, where r and s are my roots. So this is going to be a x minus, so we have to be careful, remember the brackets here. 1 plus root 7 is one root, and x minus 1 minus 7 is the other root. We do want to take one extra step to sort of simplify this. We want to get rid of those brackets on the inside. So we want to distribute the negative. So the negative that's here, we want to distribute that. So here we're going to get a is equal to x minus 1 minus root 7 and x minus 1 plus root 7. So that's the answer in factor form, and that is the family. Now we want to find the specific equation where the parabola passes through the point negative 1, 9. In other words, when it passes through that point, that means that's how we got a point on the graph, is when x is equal to negative 1 and y is 9. Another way I like to phrase it is the combination of x being negative 1 and y being 9 makes our equation true. So we go back and sort of plug that in. But before I do that, I actually want to, and I've seen a lot of people in the formative where they plug it in first into this original equation and get a, and in order to get it in standard form afterwards, it's sort of repeating the work. So what I want to do is I want to turn f of x is equal to a x minus 1 minus root 7, x minus 1 plus root 7. I just want to sort of expand and simplify that before I plug in the point. So here I'm still going to get a. So again, our trick was recognizing that x minus 1 and x minus 1, we're going to multiply that together. We could sort of group them. So here we could put an extra set of brackets and we can kind of group them. And then we're also looking to do likewise with just negative 7. Sorry, not negative 7, positive 7. And what we're going to get there is really going to see it's going to be a difference of squares. In other words, x minus 1 as a group minus root 7, and then x minus 1 as a group plus root 7. That's going to come out to be a difference of squares. So here that's going to be x minus 1 quantity squared minus a root 7 quantity squared. So doing that saves us expanding the trinomial by trinomial, saves us a lot of work. And now we're going to expand x minus 1 quantity squared, so it's going to be x squared, so negative 1 times x times 2, that's going to be a negative 2x, so that's a fast way or a speedy way to expand a perfect square trinomial. And finally, negative 1 quantity squared is going to be a plus 1, and then minus, and root 7 squared is just going to be a 7. Finally, we're going to simplify everything in the brackets, and we're going to get x squared minus 2x minus 6. So here I've created another family, another equation for the family of quadratics. In this case, it's not in factor form, but it's something that's more easier I could work with now that I have a point negative 1 and 9. So what I'm saying is that f of negative 1, in other words, when x is negative 1, minus 2 times the negative 1 minus 6, our answer here is 9. So again, use our function notation. 9 is equal to, and I'm going to start simplifying inside the brackets, or evaluating. Negative 1 squared is going to be 1. Negative 2 times negative 1 is going to be positive 2 minus 6. And finally, here I can get negative 3a is equal to 9. Dividing both sides by negative 3, and I get a is equal to negative 3. So f of x is equal to minus 3, x squared minus 2x minus 6. And this is not in standard form, so we need to distribute the negative 3 for that. So that's going to be negative 3x squared plus 6x plus 18. And that is our final answer for in standard form. The last question, we're dealing with the number of intersections of a linear and quadratic system. In other words, we have a line and we have a parabola, and we want to be able to say, well, how many places does that intersect at? So we're not asked for which the intersections are, but just how many intersections are there. So recognizing there's going to be either 0, 1, or 2. So how do we go off and determine that? Well, the first thing is we want to sort of rearrange our linear equation. So it's going to be y is equal to. Again, be careful with our algebra here. I'm going to write it out explicitly so we see what we're doing, because I saw a few too many mistakes with the negative signs. Oops, that should be not a minus 4, but it's a minus y. So here I'm going to add y to both sides. So I'm going to get 4x is equal to negative 5 plus y. And I'm going to add 5 to both sides. So I'm going to get 4x plus 5 is equal to y, or in other words, y is equal to 4x plus 5. Okay? So now that we know that this is y is equal to 4x plus 5, so again, points of intersection means that this is exactly where our two equations, where x and y, they share the same x and y coordinates. In other words, a pairing of x and y that make both equations true. So here we're going to assume that the y's are the same because that's what we want. And since the y's are the same, that means that this 4x plus 5 is going to be equal to negative 2x plus 8x plus 3. So here we get negative 2x squared plus 8x plus 3 is equal to 4x plus 5. So in order to determine what the x coordinates make both equations true, we're actually solving for a quadratic here. So it's a quadratic equation. So this is applying the skill of solving a quadratic equation to the specific context or application of where these two lines or equations intersect. So I'm going to subtract 4x plus 5 to both sides. So here I'm going to want both sides to be equal to 0, because what I want eventually is look at the discriminant. Since I want to know the number of solutions, and there are a number of x values that make this equation true, which tells me the number of x values that make both equations true in our system, we're going to use the quadratic formula in the discriminant, because the discriminant will tell us how many solutions there are. So here we get minus 2x squared. 8x minus 4x is a positive 4x, and then 3, sorry, it should be subtracting 5, not adding 5. Silly me. Let me fix that up. Minus 5, so 3 minus 5 is a negative 2, so that's 0 now. One extra step that I could do to make my life a little bit easier is that I could factor out a negative 2. So it's going to be x squared minus 2x plus 1 is equal to 0. And so here the 2's really cancel out, or 2 is gone because I can divide both sides by 2. That's the lovely thing about having one side of the equation being equal to 0, is on the other side I can multiply and divide by anything, and the right side is still going to stay at 0. So now I'm left with x squared minus 2x plus 1. Oh, wait a minute, I recognize that this is actually a perfect square trinomial. So I don't even need the quadratic formula, because here I know that x is equal to 1. There is only one solution. And that solution itself is x equals 1. Not necessary to answer this question. So that implies that there is going to be one intersection, one point of intersection. Okay. You could have gone and plugged in the original equation, negative 2x squared plus 4x minus 2, use the quadratic formula, use the discriminant, b squared minus 4ac, determine that, if memory serves me right, would have got 16 minus 16, and that would equal to 0. So in other words, the discriminant would have been 0, and that tells us there's only one solution. Therefore, in this context of this question, there's only one intersection.